Hi students, welcome to physics class. Today we will discuss about Kirchhoff laws and how to apply these Kirchhoff laws to Wheatstone bridge in order to obtain the balancing condition for it. Basic laws that governs linear electrical circuits are Ohm's law and Kirchhoff law. Ohm's law is used to calculate the current in the simple circuits, whereas the circuits consist of many branches, that is, in complicated electrical circuits, we use Kirchhoff laws. Let us recall what is Ohm's law. Ohm's law states that when there is a current passing through a conductor and the potential difference between the two ends of a conductor is V, then the Ohm's law gives the relation between the current and potential, which is nothing but V is equal to IR. Here V is called as voltage and I is called as current and R is called as resistance. The unit for voltage is volt, the unit for current is ampere, and the unit for resistance is ohm. Kirchhoff's law is used to calculate the current in a circuit which consists of two or more number of EMF sources, whereas Ohm's law is used to calculate the current in a circuit which consists of a single EMF source. That is, Ohm's law is used to calculate the current in the simple circuits, whereas Kirchhoff law is used to calculate the current in a complicated circuits. Before going to the topic of Kirchhoff laws, let us understand what is meant by junction and what is meant by loop. Junction is a point in an electrical circuit at which there exist two or more branches meet together, and loop is a closed path in an electrical circuit. Let us understand Kirchhoff first law and second law. Kirchhoff first law is applied at the junction. So Kirchhoff first law is called as junction law. Kirchhoff first law also deals with currents, so it is also called as current law. Kirchhoff first law states that the sum of currents entering into the junction, that is I1 plus I2 plus I5, is equal to the sum of currents leaving the junction, that is I3 plus I4 plus I6. In the first law, the conservation of charge follows. Conservation of charge. Second law is applicable to the loops. So, second law is called as loop law. It also deals with the voltages, so it is also called as voltage law. It states that the sum of potential differences across any closed loop is equal to 0. The first law also stated as the algebraic sum of currents at a junction is equal to 0. The algebraic sum of potential across any closed loop is 0 is the second law, and the first law states that the algebraic sum of currents at any junction is equal to 0. Here let us calculate the potential drop here IR1, because V is equal to IR from Ohm's law, so we can able to calculate the potential drop at the resistor R1 as IR1. Here the potential drop is IR2 and here the potential drop is IR3. The potential drops across the resistors, the sum of potential drops across the resistors is IR1 plus IR2 plus IR3 is equal to the EMF of the source. Therefore, E minus, by taking I as a common, R1 plus R2 plus R3 is equal to 0, which is nothing but the algebraic sum of potential across any closed loop is equal to 0. Here, the second law follows the conservation of potential differences. Here, the potential difference is conserved, whereas in the first law, the charge is conserved. Now, let us try to derive the balancing condition for Wheatstone bridge by using Kirchhoff laws. Wheatstone bridge consists of 4 resistors P, Q, R and S, and also it consists of galvanometer and an external voltage source, that is a battery. Here in a Wheatstone bridge there exist 4 junctions. Junction 1 is A and junction 2 is B and junction 3 is C, and finally the 4th junction is D. The current passing through the circuit is I. So let us write down the components in a Wheatstone bridge. It consists of resistors P, Q, R, S. Resistors. G, a galvanometer. And A, B, C and D are junctions. I is the current in the loop and E is EMF or battery. And also here there exist closed loops, 2 closed loops. Those are A, C, D, A and C, B, D, C. Closed loops. Now let us apply Kirchhoff first law at junctions and apply Kirchhoff's second law in the loops, closed loops. Here in Wheatstone bridge we have 4 junctions apply Kirchhoff first law at these junctions. By applying first law at A. At junction A, the current I is passing through the junction, passing into the junction, and again the current is divided into two paths. First one is I1 and second one is I2. So the sum of the currents entering the junction is only I, and the sum of the currents leaving the junction is I1 plus I2. Similarly, at junction C, the sum of the currents entering the junction is only I1. The sum of the currents leaving the junction are I3 and IG. So therefore, I1 is equal to I3 plus IG. In the same manner, at junction D, the sum of the currents entering the junction is IG and I2. So IG plus I2 is equal to the sum of the currents leaving the junction is I4. Finally, at B, the sum of the currents entering the junction is I3 plus I4 is equal to the main current I. These are the four equations which we get by applying Kirchhoff first law. Now, by applying Kirchhoff second law in a closed loop ACDA, we get the potential drop across the branches can be calculated by using Ohm's law. V is equal to IR. Across this branch, the potential drop is I1P. Along this branch, the potential drop is Ig into G. Here G is the internal resistance of the galvanometer, and along this branch, the potential drop is I2R. Here we have to consider the signs. We are calculating the potential drop across the closed loop. We are moving from A to C and C to D and again from D to A. The currents which follows the path is taken as positive, and this is also positive, and the currents which is opposite to the path is taken as negative. Their sum, algebraic sum, must be equal to 0 according to Kirchhoff's second law. I1P plus IgG is equal to I2R, which is equation number 5. Again, in C, B, D, C closed loop, we will apply the Kirchhoff's second law. The potential drop across the branch CB is I3Q, and across the branch DB the potential drop is I4S, and along the branch DC the potential drop is IgG. We have to take the sign conversion here. we have to calculate the potential drop across the closed loop from C to B, B to D, and D to C. So along the path, the potential drop is taken as positive, and along this path, the current is flowing against the path we have taken, so it is negative. And in the branch DC also, the current is flowing in an opposite direction, that of the direction we have taken to calculate the potential drop. So it is negative. So the algebraic sum must be equal to 0. That is, the potential drop along the branch which follows the path is taken as positive, and the potential drop along the branch in which the current is flowing in opposite direction is taken as negative. Next, I3Q is equal to I4S plus IgG. Equation number 6. Wheatstone bridge is balanced only when the current through the galvanometer is 0. That is, there is no deflection in the galvanometer, then the current in that galvanometer becomes 0. Then only the Wheatstone bridge is balanced. By substituting Ig is equal to 0 in the above equations, I1 is equal to Ig plus I3 implies I1 is equal to I3. Similarly, I2 plus Ig is equal to I4 implies I2 is equal to I4, and I1P plus IgG is equal to I2R implies I1P is equal to I2R, because as Ig is equal to 0, Ig into G becomes 0. Similarly, I3Q is equal to I4S plus IgG implies when Ig is equal to 0, this term becomes 0. Therefore, I3Q is equal to I4S. By dividing these two equations and substituting I1 is equal to I3 and I2 is equal to I4, we get I1P is equal to I2R divided by I1Q is equal to I2. Yes, I2 gets cancelled, I1 gets cancelled. Therefore, P by Q is equal to R by S, which is the balancing condition for Wheatstone bridge. By using this balancing condition, we can able to calculate the unknown resistance in the circuit.